So in Unit 3, we're going to cover polynomial and rational functions. This first bit before fall break, we're going to be focused on the idea of limits. Right at the end, we'll start in on a couple things that we will review when we get back from break. But we're going to completely cover limits before break. A limit is the y value the function approaches as x approaches a given value. For all of our continuous functions, yes, ma'am?
Do you have to bring this book back with us every day?
No, you do not need to bring it with you to class every day. Good question. The books can go home and stay home for reference. I will have books still here in the room if you ever need to reference one while you're in the building, but you don't need to bring it back and forth with you every day. Good question. All right. For continuous functions, for functions that we can draw without lifting up our pencil, when we're looking for the limit, the y value, we just plug the x value in. We just substitute it in and find out what kind of output we get. The issue comes when we have some non-continuous functions. So we're going to practice looking at a couple of these. We're going to look at a couple of them that are written as limits like this with a function rule. And then we're going to do some looking at graphs, and then we'll revisit this idea after we've kind of seen graphically what's going on. All right, so easiest way to find a limit is to substitute in. If we substitute the x value that they gave us in, and we get an output, that is the y value that it is approaching. So let's practice with part A here. Underneath the limit is where I go looking for the x value that I'm going to substitute in. So we're going to sub -4 in the place of x. All right, so my function rule is 2x plus 8. So I'm going to have 2 times -4 plus 8 over x minus 9, so -4 minus 9. What will I have in the numerator? 0. I'm going to have 0 over -13. 0 over -13 simplifies to what? Just 0. That is my limit. So I'd come up here and say the limit is equal to 0. On part B, when I take that same approach, this time I'm going to sub 2 in the place of x. We have 2 squared plus 3 up in our numerator over 2 squared minus 6 times 2 plus 8 down in our denominator. So how will the numerator simplify? 7. And how about the denominator? 0. Is this something that we're okay with? No, this is undefined. And when we have something that is undefined, we say the limit does not exist. It does not have a y value that it is approaching. And we'll look at a graph. I'll show you the different things that can happen when we have this undefined situation. Yes? This is a situation where it would be running into an asymptote. Yes. It would be running up. The asymptote is falling right at 2. So as we approach 2, the y values are either sharply increasing or sharply decreasing. but they're not approaching a single value. So we say our limit does not exist. While we're right here, I do want to go ahead and point out that if we get something like 0 over 0, that means there's a hole. When there's a hole in our graph, if we're approaching the x value, think of it almost like walking along or driving along that graph, as you're approaching that x value, it is approaching a y value, but because there's a hole, we never arrive there. But there still is a limit, because remember, the limit is the y value it is approaching. So if we run into a situation where we get 0 over 0 and there's a hole, we're going to factor so that we can cancel. And then we can sub in again after we've canceled out where that hole is to find our limit. I want you guys to give part C a try. Just try substituting in, see what happens. If you get an output, if you can evaluate it at x equals -1, that output is your limit. Were you able to find the limit? Yes. All right, so let's walk through. We're going to have -1 squared plus -1 minus 2 over -1 squared plus 6 times -1. When I simplify the numerator, what do I get? So close. -2. We will simplify further, yes. What about in our denominator? -5. When I simplify that fraction, we get 2/5, yes. So our limit is 2/5. Part D throws a little bit of a wrench in things. With all the others, we had a specific x value that we were approaching. What are we supposed to approach on D? Infinity. I can't sub in infinity. But what I can do is I can try larger and larger values of x. stable page. Thank you. So I'm going to just start with some values of x, and then we're going to increase by powers of 10 and see what's happening to our y value. Because the y value is either going to get really, really, really big, going up towards infinity. As my x's get bigger, my y's get bigger. Or it's going to get really, 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 really small. As x gets bigger, y gets smaller. Or it's going to level out and it's going to become constant. And we're going to see it approaching a specific y value. All right, so I'm going to make a t-table. And let's try substituting in 1. If I substitute 1 into that expression, what would I get? Yeah, we're going to get 5. Let me scoot this over a little bit so that I have some more room for my y work. We get 5 as our output, because we would do 4 times 1 to the 5th power plus 2 times 1 minus 1. So I have 4 plus 2 minus 1. I get an output of 5. What about if I increase that to an x value of 10? 4,019. So I would have 4 times 10. I wrote to the 5th, and it should be to the 3rd. My apologies. 4 times 10 to the 3rd plus 2 times 10 minus 1. Do you guys know the shortcut on powers of 10 when you take them to exponents? So you're going to, like, on this one, 10 to the 3rd. Anytime I have 10 to a power, I'm going to have that many zeros on the end. So that would be 1,000 times 4, 4,000, plus 20 minus 1, 4,019. Let's try this again with 100. How much?
40,000.
Very close, very, very close. It's actually 4,199,000. What's happening as our x's are getting bigger and bigger and bigger? Y is getting much bigger, right? This is 4,199,000. I don't have enough room to write it out lengthwise. What do you think would happen if we used, say, 1,000? It's going to get very, very big. I'm not even going to bother computing it. I can see the pattern of what's happening here. If my x values keep getting bigger and bigger and bigger and bigger and bigger, my y values are also getting bigger and bigger and bigger and bigger and bigger. And so we say that the limit is going to infinity. The limit as x approaches infinity of 4x cubed plus 2x minus 1 is infinity. Is infinity a number or a concept? It's a concept. Can we ever actually arrive at infinity? No. In pre-calculus, to make sure that you understand the concept of limits, if my y's are getting bigger and bigger and bigger, I'm going to say my limit is infinity. If they're getting smaller and smaller and smaller, we'll say the limit is negative infinity. By the time you get to calculus, you just say the limit does not exist. But in here, because I want to know that you understand which way our y is going, we're going to call them negative infinity and positive infinity if there is a limit there. Okay? So now that we have a bit of an understanding of what we're doing, I want to look at some graphs. We're going to analyze this graph. I've got 9 different limits that we're going to look for, 9 different things. I've got them broken down 3 per slide so that I don't get too much going on my screen. Colors can be really, really helpful if you have access to colors right now. What does this notation mean to do?
X equals 2.
Yes, we're going to evaluate the function at x equals 2. So I'm going to go over to 2 on the x-axis. They don't have all the numbers labeled here, but it starts at 0 and then 1, 2, 3, 4, 5, 6. Okay, so I filled in those missing pieces. What do you notice about when x is 2?
Discontinuity.
There's a discontinuity there. Yes, ma'am. Oh.
I was gonna say,
Yes, it's got a jump discontinuity. Look very closely on your page, because not both of them are filled in. We have this dot here, and then up here I have this dot. If I substitute in 2 for x, which one would it evaluate to?
3.
Yes, the upper one. Which they don't even have my y-axis fully labeled. Here's 1, 2, this is 3, and then 4. They're counting every other line. Here's my filled in dot. And so it would evaluate to 3. This notation on parts B and C, it says 2 and then it's got a negative, but it's kind of up almost where an exponent would be. This is telling me what direction I'm going to approach this x value from. Negative is going to be on the left side. Positive is going to be on the right side. So we are going to approach x equals 2 from the left. Again, that's what that little negative just after the 2 is telling me. That's giving me my direction. So here's 2. If I'm approaching it from the left, then I'm on the left side of it, and I'm moving in this direction. So approaching it from the left would be moving this way. What y value am I getting closer to the closer I get to x is 2 from this side?
1.
I get to a y value of 1, an output of 1. There we go. Look just at the notation here on part C. What does the notation seem to indicate I'm supposed to do? Approach from the right. We are going to approach x equals 2 from the right. So I'm on the right-hand side of 2, and I'm going to go backwards. So I'm approaching it this way. What y value are we approaching if I do that? 3. If it doesn't have the little plus or minus after it, then we're approaching it from both directions at the same time. And if I'm approaching the same output, the same y value from the left and the right as I get closer and closer to that x value, then we say it has a limit at that point. When I approach it from just the left, my y values are getting closer and closer and closer to 1. When I approach it from the right, My y values are 3. Am I approaching the same y value as I move this way from the left and the right?
No.
No. So if you look at the next one at the top of the next column, I can't remember whether yours are going columns or rows. Rows, okay, sorry. Drop down to the next row then. It says we're going to approach 2 from both directions. But when I approach it from both directions, I have this jump discontinuity here. So the limit does not exist. If we are not approaching the same y value from the left and the right, then the limit at that specific number does not exist. What's the notation in part E asking me to do? I'm sorry, just a little louder. Yes. We want to evaluate. I want to know what is the output here. When you go to 3 on the x-axis, if I wanted to evaluate this, what would the output be? 2. Right here, I've got my filled in dot. What is part F asking me to do? Approach from the left. We're going to approach x equals 3 from the left side. So that means I have to start on the left side of it, and then I move closer to x equals 3. So I'm going this way. I'm approaching from the left. What y value am I going to be at as I approach from the left? 3. Jump to the next row for me. What is that one asking you? Approach from the right. Are we approaching the same thing when we approach it from the right?
No.
No. So again, when I see that plus sign after the number, it's telling me what direction I'm approaching it from. Approach x equals 3 from the right. So I'm coming at it this way. What y value are we approaching? 2. Two more on this picture. G of 4. What does G of 4 mean? Yes. evaluate the function at x equals 4. So I'm going to come over here. Here's 4 on my x-axis. I'm going to follow that up. And one of the things that I notice is that right here my function is actually continuous. What is the y value that we've approached? 3. Remember, my limit is my y value. Which directions am I supposed to be approaching on this very last one on part I? Both sides. We're going to approach x equals 4 from both sides. So I'm going to use my fingers to actually do this. On either side of 4, and I'm going to get closer to 4 from either side of it. Am I approaching the same y value as I do that?
Yes.
Yes. What is that y value?
3.
3. Absolutely correct. We approach the same y value, the same output from both sides. Nice work. If you flip the page, we're going to look at a couple more graphs. Limit as x approaches 4. Where is 4 on this graph exactly? It's kind of a fuzzy graph.
To the right.
To the right over here. So I'm looking right there. Right at x equals 4, if I'm standing here, does the limit exist if I approach it from the left and the right? Yes. Can I stand to the left and to the right of this? And I can approach that x value. What is the y value right there? 2. So my limit as I approach from both sides is 2. Are we approaching from both sides on the next one? No. It only wants me approaching from which side? Just the left. Approach from the left. If I'm approaching it from the left, I keep repeating this because it tends to be a bit of a confusion point. That means I start off farther to the left and then I move towards that number. So if it says from the left, I start on that side of the number. If it says from the right, then I start on the right side and I have to move backwards. So I'm going to approach x equals 3 from the left. So I start off on the left side of it, and as I approach 3, what's happening?
Going down.
It's going down forever. Negative infinity. Is the same thing true if I approach it from the right? No. If I approach from the right, I'm going this way. What is the output I'm approaching if I come at it from the right? 2. What does that bottom notation mean? From both sides. So we are going to approach from both sides. If I approach from the left of 3 and from the right of 3, am I approaching the same output there? So how do I say that then? Does not exist. The limit does not exist. All right, same picture, 4 more questions. What am I approaching, and from which way? 0 from the left. As I approach 0, I start to the left of 0, and I'm noticing what's happening over here. It's going down as I approach 0. Does it stop going down? No, it's got a little arrow there. It's kind of hard to see on this printout, but there is an arrow there. So this is approaching negative infinity. It goes down forever. What about number 6? Approach it from the right. As I approach 0 from the right, what do we have happening here? Goes up forever, so it's approaching positive infinity. So what about when I approach it from both sides? Does not exist. Ooh, limit as x approaches infinity. So what happens as my x's get bigger and bigger and bigger? As we move to the right forever, yes. I notice that this has an arrow. It tells me it's going to stay flat. It's going to stay constant forever. And I want that y value, the output, that is up at a height of 4. Give me a real quick thumbs up, middle, down. How are we feeling so far about what we're doing with the limits on the graph? Beautiful. Okay. What about as I approach negative infinity? Yeah. So I'm going to go left forever. And on this graph, it indicates that it's going to go up as I do that. And because of the arrow, when is it going to stop going up? Never. So I would say positive infinity. Am I approaching 2 from the left here on the next one?
No, it's approaching -2.
We're approaching -2. From which side? Both sides. Approach -2 from both sides. So if I approach -2 from the left, and I approach -2 from the right, what y value am I getting closer to as I get closer to that x value? 3 on both sides. But there's a hole right here. It does not matter when I'm talking about the limit. A hole does not matter when I'm talking about the limit, as long as I am approaching the same y value from both sides. If we filled that dot in, could my fingers meet? If that's the case, then a limit exists. If I'm running my fingers together and we filled in those dots, but my fingers are still very far apart vertically, then the limit does not exist. What about 11? Why not? Yeah, if I'm approaching it from the left, the output appears to be getting closer to 2. But if I approach it from the right, the output is up at 4. Since I'm approaching it from both sides, I have this jump discontinuity here. My limit does not exist. What about -5? Does that limit exist? Yes. If I approach -5 from the left, I approach -5 from the right. It is continuous right in there. What is that y value, ballpark?
-0.5.
Yeah, looks like -0.5 or -1/2. If it's not falling nicely on a number, make your best guess as far as what that decimal would be. All right. Just a couple more with this same graph where we're going to look at discontinuities. Is the function continuous at x equals 0? No. That would be right here. If not, then what type of discontinuity is there? Infinite discontinuity. You guys okay if I just write DISC for discontinuity? Okay. When there's an infinite discontinuity, the limit does not exist. Is the function continuous at x equals -2? No. What kind of discontinuity is there? Removable discontinuity. Or a hole. These limits will exist. Is the function continuous at x equals 5? No. Over here at x equals 5, what kind of discontinuity am I looking at? Jump. Does the limit exist with a jump discontinuity? No. Let's go ahead and stop there for today. We'll finish up the rest of this notes packet when I see you guys again on Thursday. I don't see you tomorrow because of PSAT testing. Freshman through junior will be in the building doing PSATs. Your room assignments will be up when you get into the building. Teachers will help you find the room that you're supposed to take the test in. Seniors will not report to the building. Books, go ahead and take those home tonight. It's okay to leave them at home. The homework that I passed out, it is a front and back. That is due when I see you guys on Thursday. So you'll bring that back with you complete. And then we will continue talking about discontinuities. Sorry, not discontinuities, limits. Although discontinuities do show up here.